Hi folks, welcome back to Physics with Captain Rod, making another video here about flux. This one's going to be about magnetic flux. So I got a picture of a standard bar magnet here with a dipole field around it. And these aren't the best field lines I've ever drawn, but good enough for this example. So we're going to imagine a little hoop here with a 0.01 centimeter radius. And imagine that we put this hoop in here somewhere at a location where the magnetic field intensity is 0.5 Teslas. And I'm just making these numbers up off the top of my head here. If it were closer, field would be stronger. Out here, the field would be weaker. We're going to imagine at the location where I put this hoop, this is the field strength. And we're also going to imagine that this hoop is rotated 30 degrees. So that the angle between the magnetic field, which is this way at that location, and normal to the surface area, right, that angle right there is what I'm talking about, 30-degree angle here. Now, in truth, the field intensity is not constant along this axis. As we move further and further out, the field's getting weaker and weaker, but we're just going to treat it, this is a small distance here. We're going to treat it like the magnetic field is constant at 0.5 Teslas at this location. So think now about vector components. This magnetic field vector has a component this way in the direction of the normal. So that's B parallel to the normal. And it has a component this way, and that's the component that's perpendicular to the normal. When we calculate flux, this is the component that's going through this area. So the magnetic flux through that little circle is equal to the field strength, 0.5 Teslas, times the cosine of 30 degrees, because this component here is adjacent to the 30-degree angle, times the area of that little hoop, pi times 0.01 meters squared. And I'm going to take a moment here and grab a value here. Let's see. Give me a moment here. Okay, so I got a pretty small number, and that's okay, 0.00014. Units you can always take at face value, Tesla meter squared. So there's an example of calculating a magnetic flux. And again, some important things to realize about our little circle here. If you don't mind, I'm going to kind of reproduce it. That flux depends on the field strength in the area, but also orientation. So if I take that circle and I put it like in this vicinity, the flux would be kind of a maximum value. And as I rotate it, the flux is getting smaller and smaller and smaller until at this orientation, the flux would be 0. So just something I wanted to go over in this video. One, how magnetic flux is calculated, and its dependency on orientation. So hope that this helps. Have a great day.